Hello, my name is Jacopo Giaretta. I'm a student from the Center of Advanced Food Engineering, which is in the University of Sydney. And today, for the IEEE Sensor 2021 conference, I'm going to present my paper on flexible enzymatic sensor for the detection of hydrogen peroxide. Let me share my screen and my presentation. Here we go. So first of all, where can we find hydrogen peroxide? Hydrogen peroxide can be found in industrial applications, pretty common chemical, can be used as a bleaching agent or for sterilization purposes. It can be found also in the environment, not only as a waste from industries, but also as a product of biological reactions. And similarly, it can be found also in the human body. It can be found, for example, in blood and breath. We want to focus on, especially on food and health and environmental applications. So as you can see here, I put some examples and their range. So in what range hydrogen peroxide is present in these media. You can see there's breath, blood, drinks, aquaculture industry, some water sources. And most of these applications have hydrogen peroxide concentration mainly in the micromolar range, so from 1 micromolar to 1 millimolar. All these applications, so food, health, and environment, require the sensor to have some criteria, some parameters. One of them is flexibility, especially for food packaging and for wearable sensors. Biocompatibility and non-toxicity are fundamental for all these kind of applications. Printability, or at least scalability, is also really important. The fact that the sensor should be electrochemical is driven by the necessity of quantitative measurements, which are easier in electrochemical sensors. And of course, the sensor need to be sensitive and selective. How do we plan to achieve this? Is by combining PDOPSS, which is a conductive polymer, with horseradish peroxidase, HRP, which is an enzyme that reacts with hydrogen peroxide. We plan to combine these two with paper or hydrogel. Why we decided to use this is because we noticed that when a solution of PDOPSS and HRP was exposed to hydrogen peroxide, this caused a difference in resistance. Now, when we analyzed these solutions through Raman spectroscopy, we found out that hydrogen peroxide had also an effect on the main peak of PDOT, as you can see in the figure. Now, our right shift indicates the increase in presence of the benzoic structure, which is coil-shaped and less conductive. On the other hand, an opposite shift indicates the increase in quinoid structure, which is linear and more conductive. After having found that, we decided to proceed with preparing our solid samples. First of all, we started with paper. So we prepared an ink by mixing HRP and PDOPSS. We printed on paper, we let it dry, and then on top we printed silver inks to make contacts and make it easier to apply the clips from the potential stat. This is how a sample looked like after being cut. To assess its performance, we measured the resistance before the sensor was exposed to hydrogen peroxide. We added hydrogen peroxide in liquid on top of the sensor, we let it dry, and then we measured the final resistance. From this, we calculate the difference in resistance in percentage. The data and the results obtained are shown in the graph. You can see there are both the data for samples without HRP and with HRP. And as you can see, there is a first region where at increase in hydrogen peroxide correspond a linear decrease in resistance, but only when the enzyme is present. However, after reaching hundreds of micromolar of hydrogen peroxide, this trend is inverted and the resistance increases. Interestingly, this happens not only when the enzyme is present, but also when the enzyme is not there. So these made us think of a detection mechanism divided into two regions, as shown in the graph. The first one, for low concentration of hydrogen peroxide, requires the enzyme to react with hydrogen peroxide and favor the quinoid structure. The second one, with high concentration of hydrogen peroxide, we have the hydrogen molecule, hydrogen peroxide, directly affecting the petal structure and favoring the benzoyl conformation. These, of course, have the results of affecting the resistance. After testing in liquid, we decided to test the sensitivity of the sensor to hydrogen peroxide in vapor phase. So what we did, we devised this setup. In the first chamber, we have a solution of water and hydrogen peroxide, while in the second chamber, we have the sensor. So when we pour jam, the vapors from the first chamber reach the sensor. What we found out at the beginning was that the sensor was affected by the humidity level. So to differentiate the effect of humidity on the resistance from the one of hydrogen peroxide, which is the one we are interested in, we decided to have a first phase of humidification to reach 100% of humidity, and only then add hydrogen peroxide to the first chamber. From this, we obtained this graph. So as you can see, pouring air and not having the humidification phase decrease the resistance slightly, and that's because humidity decreases. On the other hand, if we reach 100% humidity and then we continue to purge water vapor, the resistance is almost stable, and that's because, as I said, we reached already 100% of humidity. However, if we start adding hydrogen peroxide in low concentration, in this case around 600 micromolar, we have a decrease in resistance only when the enzyme is present. Similarly to what we saw in liquid, when the hydrogen peroxide concentration increases, we have an increase in resistance in both cases, so with and without the enzyme. As you probably have noticed, these resistance variation are smaller compared to the one in liquid. This may be due to the fact that the nominal concentration of hydrogen peroxide reported in the graph may be different to the one that actually reaches the sensor. At the same time, the sample was not optimized for this application, so this might be another cause. I want to repeat that since the sensor was affected by humidity, and we wanted to try and avoid this effect, we decided to change paper with hydrogen. So we decided to use a hydrophilic polyurethane, HPU, and similarly, we mix it with HRP and PWSS. We cast it, and then we let it dry. We rehydrate it, and we obtain a film similar to what you can see in the picture now, and then we would cut it into strips. However, when we tested, similarly to what we did with paper, so in liquid, we had, yes, similar trend to what we've seen before. However, as you can see, we have large error bars, like massive error bar, which is not acceptable. This might be because to the fact that the hydrogel being soft does not allow the clips to compact properly. And it might also be because it's hard for us to control the sample water intake. Now, to solve this issue, what we did was made thicker sample to improve the contact and longer sample so that we could keep the sensor submerged in the solution we wanted to test throughout the whole duration of the measurement, as you can see in the picture. Now, these allowed us to remove almost completely the error bars, especially in the samples with the enzyme. However, this also had an effect on the detection range, as you can see here, and the detection range shifted towards the right and is also a bit wider. So it goes now from 600 nanomolar to 6.13 millimolar. Summarizing everything, I bring out again the graph with the application ranges, and because I want you to see where our sensor is sitting. So the paper-based sensor achieved a maximum resistance variation of -57%. However, this sensor was affected by humidity, so it can only be used in controlled environment, but was also able to detect hydrogen peroxide in vapor phase. So according to these ranges, this sensor could be used, for example, for detecting hydrogen peroxide in breath. On the other side, we have the hydrogel-based sensor. Although this sensor achieved almost half the maximum decrease in resistance, this sensor could be used in continuous monitoring of solutions and liquids. which allow the sensor to be used in applications such as environmental monitoring of water, and for example, for blood, or for food applications such as aquaculture industry. Now, at the end, I want to thank and acknowledge all my supervisor and my research team, the members from the Center of Advanced Food Engineering and the University of Sydney, and also the financial support from the Australian Research Council and the Lockstone Postdoctoral Fellowship. If you're watching this video, I'm not probably there to answer your questions. So if you want to send me an email with your question, I would be really happy to answer them. And thank you for listening.